Hey guys, I wanted to show you a few different things that have to do with sound and music. Um, there's not a whole lot more mathematics we have to do in this chapter, but these are kind of the last couple things I wanted to show you about sound. Um, we watched the video yesterday or earlier this week about beats and beat frequency, which is really hard to do a demonstration of from my home, but I hope you like that quick video of the guy showing you some beat frequencies. I want to talk about a couple different more musical sort of phenomena, and then I want to show you kind of how we're going to review for our quiz on sound, which will be next week. So I'll go over a couple terms and I'll show you how we're going to kind of do our whiteboard problems as well for our review. So we did this little lesson about beats. We said that if two different frequencies are played at the same time, what ends up happening is that they at one phase kind of cancel each other out when we say that they're out of phase with each other. But then when they, after some time passes, they get more closely aligned and they're in phase. What we learned about interference is that if two sounds are sort of overlapping, two waves are overlapping, the amplitude or the intensity is, in the case of sound, is going to get much larger. Whereas when they're out of phase, they're canceling each other out. So what's the wavelength of this, or what's the frequency of this larger wave? Well, it's always just the difference between the two. And that's what you hear is a wah, 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 wah when something's out of tune. So by the way, the equation for beats is just the difference between the two frequencies is called the beat frequency. So whatever two frequencies you're hearing, the absolute value difference between those two is the beat frequency. When we're tuning something, we can hear a note played by a clarinet or a piccolo or a violin or whatever, and you can tell that it's what instrument it's coming from, even though two different instruments are playing the same note, which is sort of a bizarre thing to recognize. And people had for a long time, had a hard time describing this. How do you know if I'm hearing an F from a clarinet or from a violin or whatever? And the reason you can hear this is because of a phenomenon called timbre. Let's see. The timbre of a sound is just the musical quality that you hear. So the timbre comes from the Latin word, which really just means the sound or the noise of something. If you're in Spanish, el timbre de la puerta is doorbell, the sound of the door. So it just is a Latin word meaning sound, but we pronounce it in English, we pronounce it timbre. So the timbre has to do with the combination of the different harmonics that you hear at different intensities. So I showed you in class before we went on stay-at-home teaching, I showed you a tuning fork, and I kind of walked around and I put it right up to your ear. So you play a tuning fork, and it really just plays. There's not really much what we call twang in a tuning fork. All you really hear is just the first harmonic of the tuning fork, of just the vibration frequency of just the aluminum or steel or whatever going back and forth. All you really hear is that first harmonic. And so that turns out to be a nearly perfect sine wave of just that one frequency. Other musical instruments are actually much different. You tend to hear a combination of different harmonics. Supposedly with a piano, you can hear like 10 or 12 different harmonics at the same time. But this is what kind of gives them their different sort of qualities. Like, for example, a clarinet may have a very intense first and third harmonic, but a relatively quiet second and fourth harmonic. Whereas a viola or violin might be relatively intense first and second harmonic, but hardly any third or fourth, and so forth. So it just depends on the intensities of the different harmonics you hear. So we know this to be true. So I have my little MIDI player here where I'm going to kind of switch instruments as I kind of go through and play the same note. So I'm just going to play, kind of select a note at random. I'm going to select A. So I have the sound selected as tubular bells, but you'll be able to tell that the instrument is changing, but the note isn't as I kind of switch back and forth. So you can tell that they're all different instruments, even though I'm playing the same note every time. So that's what we call timbre. That's the musical quality of something. Every note, if for those of you that play an instrument, you probably are a little bit more familiar with this. When we I can't fit both of these things on the screen at the same time. When we put notes on a piece of music, we're sort of declaring what note to play on a piano or trumpet or whatever. But actually what we're showing is a frequency that we're going to play. So every note corresponds to a certain frequency. As long as the two instruments are in the same key, both of them playing the same, like this is middle C, we call it. If both of them are playing middle C, they're both playing the same basic frequency there. Now we just said there's other harmonics in play, but the main note that they're playing is that same frequency, which corresponds to a set number. For example, so middle A, this is a couple notes lower, is always 440. We use this as an example because it's really one of the only whole number frequencies. Almost all of them are some sort of bizarre fraction or decimal. And so you know this from, if you ever watch The Sound of Music, you might know the song Do, Re, Mi. So this is a key, the way that we sort of aligned the musical notes. Well, I mean, for hundreds and hundreds of years, people have known this to be true, that certain notes kind of sound good together. I'll go back to the piano for just a second. So if I go, I'm going to play starting at this C, which is middle C, and I'm going to go all the way up to the next C. And you'll kind of probably recognize this as sort of the Do, Re, Mi. Oh, let me change to a better instrument here. So the reason I selected those is I know that these are kind of, I just selected the key of C here, but I could just as easily do it a different way and do a Do, Re, Mi starting at a different note. It doesn't have to start at C. I could start at this one. I could start at B flat. And you realize, well, I had to play kind of some different notes. I kind of went around there. The reason that I had to do that is there's always a set number of steps in between each note. And sometimes you include certain notes and sometimes you don't. And so the way the musical pattern is aligned is that there are what we call 12 half steps. So there's sometimes, so these would include the black keys. So on a piano, every time you go from one key to the next possible key, that's a half step. And sometimes there isn't even a black key in between, like E and F, that is a half step. And you work all this out and you realize that there's a really important property here, that you're kind of getting back to the same note. So I just went C to C. You're getting back to the same note. How are both of these C, but they're two different frequencies? Well, this is what we call an octave. An octave is when you go through the notes and you get back to double that same frequency. So if I went from C to C or A to A, what I'm really doing is I'm going all these different steps in between. If I went from A to A, I'd be going from 440 hertz all the way up to double that same frequency, 880 hertz. But this is true for every note, not just A. It's true for B flat or C or whatever note you want to choose. The next time you get back to that same note, it's always double what the frequency was to begin with. So if I start with 440, the next octave will be 880, and so forth. If I started with some other bizarre decimal, it would just have to be twice as much. So for C, it's actually an irrational number, but 261.62, and you work out the math, and I double it to get to the next C, and that would be 523 hertz. And then the next one after that would probably be 1,046 hertz, and so forth. And those would all be C's because I can just keep doubling it. Now these ones in between are, there's some notes that kind of sound good together and some notes that don't. And some notes kind of sound harmonious, we say. And the reason that those sound harmonious is that they are actually, those notes may not be double or quadruple the frequency, but they are what we call perfect intervals. So those are actually because you may be playing the third and fourth or the fourth and fifth harmonics. So we call those perfect intervals. Let me show you an example of a perfect interval. So one example of a perfect interval would be, let me see here. I go A to F would be a perfect interval. We call this a perfect fourth. So I'm going to go A to F here. Oh, I'm sorry, A to D is a perfect interval. So this is, you might recognize this kind of as like Amazing Grace. Okay, or you might recognize it as like, so you might recognize like Here Comes the Bride. So that's kind of harmonious. That's called a perfect fourth. And when I go to this one, that's called a perfect fifth, perfect fourth. Those sound really good together. But if I go to this one in between, oh, that sounds terrible. So that one is not a good interval. That's what we call an augmented fourth. And it sounds really gross. And the reason is because the beat frequency, remember the beat frequency is the difference that you hear in between the two frequencies. The beat frequency is sort of off tune with itself. So that sounds really bad, but you may still include that in a song, like if you've ever seen West Side Story. Maria, maybe you recognize that tune. So it doesn't mean you can't include it in a song or whatever, but sometimes when those are played together, the word is dissonant. So those of you who are in music class may have heard these terms before, but there's a physical reason why some things sound good and some of them don't. And the reason that you hear the harmonious perfect pitches or perfect intervals is because those are actual harmonics where you're going between like the third or fourth harmonic of the same note. They sound really good together, whereas when you're going to sort of in between two harmonics, it sounds really bad. Okay? So those are kind of the things I wanted you to know about music. So the term timbre, beat frequencies, and octave, and you should kind of also know about these perfect intervals as well. So just sort of some key words. What I wanted to also show you is how we're going to do a review for our test. So I put through some whiteboard problems. I'm attaching these as a PDF to this assignment. And what you're going to do is you can work them out on your own time. They all have a number in the corner. And some of them are just going to be a one-word answer or a fill in the blank or something like that. You can just put them on a piece of paper or a Google Doc or whatever. And what I'm going to do is next week I'm going to post the key. So I'm going to post the key on Thursday, and if you get them solved, so that's 1 week to do this. If you get them solved before Thursday, I'll give you 100% credit when I post the key. If you can get them done before the end of the day on Thursday, before the end of the school day. And then I'm going to post a quiz for sound, which will be multiple choice and some numeric answer. I'm going to post that on Friday. So if you can get that done. But if you wait till after I post the quiz to do any of the whiteboard problems, I'll only give you half credit. Okay, so sort of an incentive to review before the test. So I'll post all that. The key I'll post for all these next week. And so I'll set the due date on this assignment. So let me know if you have questions or how to work some of them out. And I will. I hope you all have a good weekend.